Okay, so it's recording already? Alright. Okay. Right, so does everybody see what's going on here? I claim that between these, so we know that these four types of edges exist. We don't know about the other two types. And I claim that one of those two types is the problem. One of those two types of edges is what creates the non-isomorphism. If you don't have one of those two types, then you can actually prove that the underlying simple graphs are isomorphic. Which type? It depends on the notation. Right? So I have chosen a certain way of shrinking things. So is it this type of edges or is it this type of edges? Which ones are the ones creating a problem? If you have figured it out, let me know, I'll come and talk to you. In the horizontal, vertical? Yeah. Those are always there.
Yeah, horizontal one, vertical one.
No, it's going to be either this or that. The horizontal and vertical one matters.
Oh.
What matters is the other two types. No, nothing. No assumption. Just bonds, connected graph, they are crossing, and that's it. Yeah. One of those two. Which one? No. Yeah. One of those two are the ones creating the problem. So it's going to be either this type of edges or this type of edges. Which of them? Those are the two. The other edges don't matter. The other edges, they don't create the non-isomorphism. Remember, we are looking at the underlying simple graphs. And we are not looking at the two graphs. We are taking the underlying simple graph. That is an important point. Okay, basically your labeling is That's okay. Degree is not a problem. The underlying simple graph could be the same, right? Even if the degrees are different, Underlying simple graph could be the same, right? You have to, yeah. So just comparing degrees will not help. Think about the exact adjacencies. Yeah. No. Yeah. Yeah. Works. Yeah. Yeah. Okay. I did not check the example. You did. Yeah.
From x bar y to y bar.
This example makes it clear actually. There's an edge going from x bar intersection y to x intersection y bar. Those are the problematic edges. That is exactly what creates the non-isomorphism between the underlying simple graphs. If those edges do not exist, then prove that the two underlying simple graphs are actually isomorphic. Yeah? So, prove that if the edges between, so I'm using this notation, x bar intersection y to x intersection y bar, if this set is empty, then the underlying simple graphs are isomorphic. I have taught this proof maybe more than 5 times. This is the first time I've been able to get this observation to this level, like where I've thrown out as many hypotheses as possible. No matching covered, no tight cut, nothing. I've tried to keep the bare minimal. I kept connected because connected is too basic. Maybe there's a hypothesis. Maybe you can also remove connected and make something more general. But I thought connected was natural. Bond also, it makes sense actually if you think about it, the proof. So I kept connected and bonds, and then I threw away all the other hypotheses. And this is what it boils down to. So, okay, so what is the good thing about this? The good thing is that if you are in this case, where there is only one cut in script C, one cut in script D, what you need to convince yourself is that the 2C contractions and the 2D contractions are basically the same up to multiplicities of edges. The 2C contractions are isomorphic to the 2D contractions in some order, doesn't matter, up to multiple edges. And that is basically this. In fact, you are not even shrinking one shore because the shore is already a single vertex. These two shores in the proof, they are already single vertex. So this is more general than this. Yeah. So if this happens, then by this TIY, the 2C contractions and the 2D contractions are isomorphic to each other as a set up to multiple edges, and the proof is finished. Yeah. The problem is, what if this is not the case? What if there are other cuts in the set? We will prove that that is not possible because none of the above cases hold. So this is where we will use the fact that because none of the above cases hold, this is exactly what happens. This is not an assumption, this is a fact that we need to prove. Okay? So, if assumption holds, done by above TIY. And now we will show that the assumption holds. Okay, I'll erase these examples if that's okay. Oh, I did not prove. No, we are not done by TIY. We need to prove that these edges don't exist. The TIY says if this set is empty, then the two graphs are isomorphic. We need to show that this set is empty. So we go back to our lemma 4.12. The lemma is not complete. There are two statements. The second statement says what you want. What do you want? There are no edges from the bottom left quadrant to the top right quadrant. This is the second statement. The x bar intersection y to x intersection y bar. This set is actually empty. This is where you need tight cuts. To prove that this set is actually empty, use the fact that these are tight cuts. Supposing there is an edge from here to here, DIY. Yeah, there can't be any such edges. Take a perfect matching containing that edge and count.
Can you tell that again, when you assume this and that?
Yeah.
How did you finish that?
Yeah. So, if I have only one cut in script C and only one cut in script D, what does that mean? That means that I should prove that the two C contractions are isomorphic to the two D contractions. That is done if we prove that this set is empty and we assume this TIY, which is a TIY. So if we prove this is empty, then by using the conclusion, we are done. Yeah? Yeah? Got it? Yeah?
Yeah, definitely.
Okay, so take a perfect matching containing this edge and you will see a contradiction to tight cut.
D is the tight
cut. Either of them, right? It's symmetric.
Yeah, either.
Either of them will work. Yeah. Because there is an even number of vertices, you are matching one outside. So one more has to match outside. So that one will either cross the blue edge, cross the blue line, or cross the pink line. But this one is already crossing both lines. So you'll get two edges either in the blue cut or in the pink cut. Contradiction because they are tight cut. Yeah. So we are done with the uncrossing lemma. We proved everything here. We did not prove the TIY. That is for you to prove. Using this and TIY, we are done. Because the two C contractions are exactly one of the C contractions will be this graph, one of the D contractions will be this graph, the other C contraction will be the same, you change the notation, the other D contraction will be similar, change notation. These two are isomorphic up to multiplicities of edges, those two are isomorphic, done. Yeah? Everybody sees that?
The TIY that prove if this is
Yes.
empty, then wait.
Yeah. Yeah. So now what we are left with is we are left to prove that this assumption holds. It remains to argue that this is not really an assumption. Yeah, it's a conclusion of things you've already assumed. Yeah, okay. Supposing this is not true, supposing it is not true that script C is a single cut containing C and script D is a single cut containing D? Well, that means one of them has one more cut. Let's say script D has another cut called F. Suppose not, and I want to take a cut that is laminar with C and will cross with D. So I will take it in. I will take it in script C, and let capital F belong to script C minus C. Supposing there is one more cut in one of the two families, adjust notation so that it is in this family and it is not the same as C. Yeah. Let's call it partial of Z. Let F be partial of Z. F is laminar with C and it crosses D. F is clearly laminar with C because script C is a family of laminar cuts. So by definition, F is laminar with C, but it cannot be laminar with D because none of the above cases hold. Yeah. So in fact, it should cross D. F crosses D. Yeah. Okay. Now here comes the interesting part. Let me make some space. So we'll finish the proof in this drawing here actually. Okay, so this is our pink cut. We don't actually need the yellow cuts, but let me just keep them, they don't matter. Try to ignore them. This is a blue cut. Okay, we have C, we have D. Now we have another cut F. It is laminar with C, but it has to cross D. Convince yourself that this drawing is not misleading. It is as general as life gets. This is the cut F. I am adjusting notation so that Z is a subset of X and Z bar is a superset of X bar. Okay? Adjust notation. So F is partial Z and let's say Z is a subset of X. Okay? What is misleading here is this. I don't know where this is. I know that U is in this quadrant. In this quadrant. Whether it is here or here, I don't know.
They are crossing, so it has to be above.
Yeah, we will conclude something. You are right. Yeah. So, yeah, I'm coming there. Yeah, if you have already figured it out, great. So, I know that U is in this box. I know V is here. Therefore, it is also here. Yeah. Okay. Everybody with me? So, we want to basically arrive at a contradiction. Yeah. So let's try to figure out where this is. Remember, F and D are crossing cuts. Therefore, all the four quadrants, let's mark the four quadrants with respect to F and D. F and D, I will mark it here. So this is going to be my Z intersection Y. Z intersection Y. This part here is my Z intersection Y bar. This part here is Z bar intersection Y bar. And this part here is Z bar intersection Y. Yeah, everybody agrees? These are the 4 quadrants I see when I intersect the pink line with the orange line. Yeah. Now I want to basically say there is a contradiction. Let's try to figure out where is the vertex U. We know that all 4 quadrants are non-empty. The only vertex here is U. Therefore, U should be here or here? Top. It has to be in the top part. If it is not here, then this fellow is empty. That's a contradiction. They are not crossing. So U is actually here. Yeah? In particular, there can't be any other vertices here, because there are no other vertices in the big box. So how can there be more vertices in the small box? Right? This is actually empty. This little sliver you see here, that is the empty set. Yeah? So U is the only vertex in Z intersection Y. Yeah? All good? Recording is not going on? Okay?
Okay. Yeah.
All good?
Yes.
Yeah? Okay? So U is the only element in Z intersection Y. That means that Z intersection Y is odd. This fellow is therefore odd. This fellow is even. This fellow is again odd. And this fellow is even. Right? No, yeah, this entire quadrant. Yeah. This is odd. This is in fact a single vertex. Yeah. Now let's think about now let's think about this part. Can this be non-trivial? Can this part, what is this, Z bar intersection Y bar, can it be non-trivial? Why can it not be non-trivial? Yeah. None of the above cases hold. If this is non-trivial, then you would have a cut in C, script C, you have a cut in script D, and one of the two quadrants, one of the two odd quadrants, at least one of the two quadrants is non-trivial. We would be in case 3. But we are not in case 3. Right? Therefore, this is trivial. That means V is the only element here. That means this fellow is also empty. Well, if everything between the orange and the blue line is empty, then the orange line is equal to the blue line. Right? So we are done. So yeah. We just proved the assumption. This is not an assumption. It follows from the fact that none of the above cases hold.